Now imagine you're given a set of edges in an image and you want to fit a line to this set of edges, or you want to fit a low-order polynomial, a curve. Let's take a look at how that's done. First, let's talk about pre-processing edge images. So here is an image of a vase, seems like a simple image, and what you want to do is to come up with a boundary detection output that looks like this. But this is highly aspirational, because this image has actually been manually sketched. It's been hand sketched. And that's why it has these very clean, clear boundaries. It's a hard problem. So what you do first is that you apply edge detection to this image, and you end up with an edge map that looks something like this, where at each pixel you have the strength or the magnitude of the edge. And then you can threshold this to get this binary image. And now you can use one of the techniques or several of the techniques we discussed in binary image processing to clean up this image a little bit. For instance, if you shrink and expand these edges, you end up with something like this. The shrinking ensures that all these isolated edges in the image just go away, and then you expand the rest of the edges again. And now, since these edges will probably look a little bit thicker than you would like, you could apply a thinning algorithm, and you end up with edges that look like this, which is cleaner than what you had back here. But now the challenge is to go from this edge map to these boundaries. And that's the problem of boundary detection. So let's start simple. Let's talk about how we can fit a line to a set of edges. So here's a bunch of edges that are given to you, xi, yi, and the problem is that we want to find the line y equal to mx plus c that best represents the set of edges. So in other words, we want to find the slope and the intercept, m and c, corresponding to the line that best represents the set of edges. So how do we pose this problem? Well, first, we're going to set up an energy function. We'll call it a cost function or an energy function. And what we want this to represent is the average of the square of the vertical distance between each point and the line that we're trying to estimate. So if you simply say yi minus mxi minus c, this right here, this expression, that represents the vertical distance of a point from the line. And so we're going to square all of those for all the points, add them up, and then divide by n. That's the average right here. So one reasonable thing to do would be to find the m and c that minimizes e. And we know how to do that. You would find the first derivative of e with respect to m, set that equal to 0. First derivative of e with respect to c, set that equal to 0, and you get these two equations. Remember, when you find the derivative, you can take the derivative inside the summation because they're both linear operators. And from these two expressions, you get closed form solutions for both m and c. They look like this. And here I should mention that x bar and y bar are the means of x and y, the data points, the edge points that are given to you. So very simple. You simply plug in all your xi, yi into this expression, you get m, and then plug that into this and you get c, and you're done. We have a bit of a problem. So let's say that you were trying to use this technique to fit a line to this set of points. What do you think that the line would actually look like? We know that the line we are looking for looks like this orange line right here. That seems to best represent, best fit these points. But it turns out that the line that you end up computing using the technique we just discussed is actually this line. It's virtually the opposite of the line that you're looking for. It's perpendicular to it. And why is that the case? Because we were minimizing an energy function that had inside of it the vertical distance of each point from the line. Well, the vertical distance from any point here to the line that you're looking for is fairly large. Let's take this point right here. The vertical distance would go all the way down here where it intersects the line. So that is not the line that minimizes the vertical distance, or the average of the square of the vertical distance. Turns out that this line indeed does that. So what this goes to say is that when you set up a fitting problem, you need to be careful how you formulate the energy function that you're actually minimizing. In other words, what is it? What is the distance that you actually are minimizing? And I think a more reasonable thing you would agree to do is not to minimize the average of the square of the vertical distances, but rather the perpendicular distances. So for that, we have to use a different parameterization of the straight line, and we're going to go to one that we have used in the past, which is x sine theta minus y cosine theta plus rho equal to 0. We used this in our lecture on binary image processing. And theta here is the angle that the line makes with respect to the horizontal axis. We know this. And rho is the shortest distance of the line to the origin. So let's see how this works. Well, now, if we use this to construct your energy function right here, E, and so now you have in here xi sine theta minus yi cosine theta plus rho. That term is the perpendicular distance of a point from the line. And that's exactly what we want. Those are these blue lines that you see right here. So it's that distance squared summed over all the points and the mean of that. And if you look at this, you see that it looks very familiar. It's actually what we were trying to minimize in the case of binary images, where we were trying to find the axis of minimum second moment, if you remember. So this is exactly that expression right here. It was called R in the case of binary images, and then we finally ended up with this expression, and you see it back here. So we know how to do this. We know that if you're given now a set of points, we can treat it like a binary image, a set of edges, you treat it like a binary image, and essentially find the axis of minimum second moment, and that is the line that minimizes the average of the square of the perpendicular distances. That's the line you're looking for. So we know how to do that because from our solution in the past, there are 3 moments A, B, and C that we end up computing from these edge pixels, and then from those 3 numbers, A, B, and C, there are simple expressions that take us to theta and rho. Okay, so now let's take it up a notch and go from straight lines to curves. So now you're given, again, a set of edge points, and you want to fit to it a polynomial. And let's say it's a third order polynomial. As an example, it can be any order. So you have y equal to ax cubed plus bx squared plus cx plus d. And we want to find the a, b, c, and d, the parameters of the polynomial that best fit the points. So once again, if you go back to our distance metric, which is the vertical distance, then it's very easy to set this up. You have an energy here, which is the average of the sum of the average of the square of the vertical distance between a point and the polynomial that you're fitting. So this expression right here, yi minus all of this, is the vertical distance of the point xi, yi from the polynomial. And let's say that's what you're looking for. That's what you want to minimize. Well, in that case, it's very easy. You find the derivative of E with respect to A, with respect to B, C, and D, set them all equal to 0, and you get a system of equations. So it's very easy to find these derivatives because even though you have x cubed and x squared and all of that stuff in here, it doesn't really matter, they're all known. This expression on the inside is linear in terms of A, B, C, D, which are the unknowns you're looking for. And so, of course, there is a square here, but once you take your derivatives, you're going to get a system of linear equations. You can literally derive this by hand. You get 4 equations, 4 unknowns that you can solve for A, B, C, and D. Now, the problem here is that given any polynomial, let's say now tomorrow you're interested in a 5th order polynomial, you'd have to go down and find these derivatives each time and then create the system and solve the system. That's sort of cumbersome to do on a case-by-case basis. So the question is there a more general technique that we can use here? And so that brings us to solving a system of linear equations. So here you can see that if you take the polynomial that you want to fit, again, in this case, it happens to be a third-order polynomial, but it could be any order. You take the equation of the polynomial, and you essentially plug in all the points in there. x0, y0, that's the first point, x1, y1, and so on. Each point gives you one equation. And the unknowns in this equation are clearly a, b, c, and d. So you have a whole bunch of equations, number of equations equal to the number of data points given to you, edges given to you, right here. And now you want to find the unknowns a, b, c, and d. So this is the problem where you're given many xi, yi. And so if the number of edges that are given to you are larger than the number of unknowns, then this is an overdetermined linear system of equations. Now let's take a look at how we can solve such an overdetermined linear system of equations in a general way. So that brings us to a math primer. So here you have your overdetermined linear system with m unknowns. So in our case, we had 4 unknowns, a, b, c, d, but now we have m unknowns, and we have n observations. The observations are given as xij, y. X has 2 subscripts right here, ij, because I corresponds to the data point itself, in our case, the edge that's given to you, and j corresponds to the coefficient in the linear equation itself. So that's what you get here in matrix form. You have this matrix multiplied by this vector is equal to this vector right here. So what is known here? Well, x is known, the matrix x is known, and the vector y is known. X is n by m, because remember it's an overdetermined system of equations. And what are you looking for? You're looking for these unknowns, which is the vector a, m by 1. So a very simple form here, you have x, a equal to y. And of course, your first instinct would be, well, we can find the inverse of x and solve this problem. But we know that x is not a square matrix, and therefore it's not invertible. So how do we solve this problem? Well, we pre-multiply this equations, both sides of it, with x transpose. And then you get this. X transpose x, a is equal to x transpose y. And now we know that x transpose x is actually a square matrix. It's an m by m matrix. So you can find its inverse and find a solution for a that looks like this. And this term right here, x transpose x, the whole thing, inverse times x transpose, is called the pseudo-inverse, sometimes given this notation x plus. So we have a equal to x plus y. This is a very general technique for solving a system over determined linear equations.